Welcome everybody. My name is, as organizer said, my name is Dendek, and I am a PhD student from HGH UST Krakow. And today I'm going to talk to you a little bit about about machine learning in the field of high energy physics. So before I start, I would like to, preparing this presentation was a really hard task for me because I have no idea about the audience. So before I start, I would like to ask you two or three questions to know a little bit more about you. So please raise your hand if you have a background in the physics. So who from you? Okay, some of them. Who from you are working as a data scientist? Who from you has experience on a GANs network, have trained or have ever at least heard about this? Okay, so most of them, most of you. Okay, so thank you for this very short conversation. So let me start. So I decided to split my talk into two sections. So first section is like introduction to the field when I'm working on. And this field is the high energy physics. And in particular, I would like to talk about the Large Hadron Collider Beauty experiment, the experiment that I am a member of. And then, then I would like to add to give you some ideas why we decided to build this detector, why we need it. And then I go to the second part of my presentation, which is the application of machine learning technique in this particular experiment. So first of all, I would like to discuss the problem of particle identification, how we enhance the process of particle identification using the machine learning. The second one, I would like to spend some time on discussing whether the Monte Carlo are the only method to simulate the data. So maybe there is another idea that we can leverage. So maybe we can use some deep learning stuff to generate reduce the computational times. And the last one is machine learning as a part of the online trigger. So first, I would like to give you some introduction to the jargon that I will be using. So online trigger, means that this is like an analysis in the real time. So you should, I don't know if you're familiar with this, but so first I would like to start with the large introduction to the field of high energy physics and to HCB experiment in particular. So first of all, what is the high energy physics? So the high energy physics, so this is like a Wikipedia style definition. So high energy physics is a branch of physics that study the nature of the particles that constitute the matter and radiation. And within this field of the science, there is one greatest achievement from the theoretical point of view, which is called the standard model. And this standard model is the theory that describes the fundamental particles and the fields. And so what are the two most important learnings from this theory? So first of them, the matter is made of the quarks and leptons, and the interaction between them are driven by the particles called bosons. Here is the schematic view of all of the known particles. And another thing that was discovered and was proved like a couple of years ago in 2012 is the Higgs mechanism. This is the mechanism that gives the particles masses. So I can talk about the standard model for at least for the half an hour or even the hour. But so this is like one of the greatest achievements in the theoretical physics so far. But it was tested for about 30 years, and there is almost no evidence that there is some processes that violate the prediction of standard model. But there is one small problem of the standard model. So there is a small gaps in the prediction of the model. So there is a still open question that the standard model doesn't answer for it. So I would like to focus on two particular questions. So first question is, so very important. So why our universe exists? So first of all, maybe, I don't know if you heard, but our universe was born in the Big Bang. So in the Big Bang, the amount of matter and antimatter was equal. And as you probably may heard, that if matter and antimatter meet each other, they will annihilate, and the outcome of this process is like only photons. So the question is, so if we've got the same amount of matter and antimatter, what should be our universe shouldn't exist. And we know that we are here, and so there should be a process that do some discrepancy, that explain the discrepancy between the matter and antimatter. And this process is called the CP violation. To explain details, it is out of scope of this presentation. So, and the second question that we are trying to answer is, what is the dark matter? So from cosmology, we know that the universe is built on some strange, let's say, thing that the cosmologists call the dark matter, but the standard model has no idea what it is. There is no particle within the framework of standard model that describe it. So what do we need to do? So we know that this model is not the final one. So we are looking for the processes that violate the standard model. That we are looking for. It is called new physics. Yes. Sorry, could you repeat? Like,
where's the antimatter in your standard model picture?
Okay, so each of these leptons and quarks has like an anti-quarks. So I just put on the slide, so the only one of it. Okay, so how we do this? So in high energy physics, we are using a very brutal approach. So we build a very big device called the accelerator. We are accelerating the particles. We are colliding them each other, like this beautiful cartoon in here. And what we wanted to achieve, we are looking at the product of this collision. So, and then if the product doesn't behave as we expect from the standard model, we said, okay, we are very happy because this is something, it's a new physics, new discovery. Okay, so let me just show you a couple of pictures how does our accelerator system works. So this accelerator system is built on top of multiple stages, but the last one is called LHC, Large Hadron Collider. You probably have heard about it. And it has a length of 27 kilometers. It is located in the border Swiss and France, very close to the Geneva, very nice region. There is the Alps in there. Okay, so we know that we've got accelerators, so we accelerate the particles. Now, what we need to do, so we need to collide them. So we collide these particles in 4 different points. And each of these points, we put some detector. So the detector is a device that needs to detect, so needs to know what was the outcome of this collision. So what was the daughters of this collision, let's say, of this collision. So, and I would like to focus on only one of these experiments, the one that's called LHCb in here, because I am associated with this concept. Okay. So let me show you another image of this experiment. So this is like a real photo in the LHCb cavern. And as you see, you've probably seen almost nothing except of the metal construction that keeps everything together. So that's why I decided to put like a schematic view of this detector. So this detector that I'm describing contains of the multiple stages, multiple of subdetectors, and each of them is responsible for the different processes, for the different things. So basically why we did this, because we are asking the detector for a couple of things. So first of all, we need to know what type of particle we are dealing. The second thing is, what is the momentum of the particles? And the third one, what is the energy of the particles? So to reconstruct it, we put some sort of the different types of the detectors. So we are starting with the velo. This is the place where the particle collide. And then we've got the bending magnet, which is used to bend, because when we wanted to find the momentum, we need to bend something. It is, okay. Okay, so let me show you the comparison of the CERN and maybe something related to the to the Google and Facebook. So, okay, so you probably understand the idea. So we are colliding the particles. We've got some daughters of, so some outcome of this, so like said, daughters of this decaying of these collided particles. And now what will be the amount of data that we collect? So the amount of the data that LHC generate is about 40 terabytes per second. So put it into the perspective, Google combined with Facebook and with the WhatsApp generate roughly 0.3 terabytes per second, which is like 2 orders of magnitudes more. So, and obviously the CERN is like a scientific institution. We don't have that amount of money like combined Google and Facebook, so we are not able to keep that amount of money and that amount of data, of course. And what else? We don't really care about lots of the events. We only care the events that are strange, that are have potential to discover new physics. So a couple of examples, the Higgs boson. There is another example that are particles that are beyond the standard, processes that are beyond the standard model, the new physics, let's say. And okay, so we need to build a system that works in the real time that will allow us to store the data. So, but the problem is, if the system makes a mistake, this trigger system, we are not able to retrieve it. Because if the system said, okay, this event is not important, not interesting, we are losing this. There is no way to retrieve it anymore. Okay, so now you've got just a little bit about our experiment. So now let me move to the second part, which is probably more important for my more interesting is application of the machine learning. So how we boost our data processing using the machine learning. So as I said, we are basically asking the detector we are asking them a couple of questions. So first of the question that we are trying to answer is, what are the type of the particle? So, okay, so how we can do this? So so some people at CERN discovered, so they proposed that the good idea for detecting the particles would be to build like a Cherenkov detector. So the Cherenkov radiation is the radiation that occurs when the particle in some material travel faster than the light. Okay, this is not possible in the vacuum, obviously, for this reason. And okay, so this process is very similar to the aircraft breaking the sound barrier, as you may see it. So and okay, so there is something and the velocity of the particle depends of the shape of the cone, which is created in here. So if we combine a little bit of information from this Cherenkov detector with some other detectors, we are able to tell what type of particle we are dealing with, and this is pretty important to us. Okay, so now how do we do? So let's say that some time ago there was a group who was working on the enhancement of this procedure using the machine learning. So as I mentioned, we've got the 2 Cherenkov detectors. One is before the magnet, and the second is after the magnet. And as well to enhance this the identification process, we use also the information from the muon chamber calorimeter system. Okay, so what we've got? So we've got the input from each of these detectors, and what we build a model. So you can think of this like a black box. And we wanted to know what was the type of this model. So basically, so this is like a multi-class classification problem, so it should be for those who are working on the machine learning something really obvious. And what type of models do we check? So first of all, first idea, very naive, very simple, was the shallow neural network, the neural network with only one hidden layer. And it was trained using the TMVA. This is this library that is very popular in the high energy physics community. And the second one idea was the deep neural network with the multiple, probably 4 hidden layers. And the one that won, let's say, this Kaggle-like competition was the boosted decision tree. So this is like another word that I'm using as a jargon, because what we are calling the boosted decision tree is basically the gradient boosted algorithm. And so and also from this moment, I just wanted to give you one recommendation. So if you are working with the tabular type of data, I would encourage you to play with the cat boost. So the cat boost is the package that was developed by the Yandex. So Yandex is the company that is a competitor to the Google in Russia, so which very successful competitor to the in this area. And it is a very nice feature that it can handle categorical variables without any preprocessing. You don't really need to encode it. They've got like a pretty sophisticated method how to do it, which works very well in many applications. So I just encourage you, if you have some time, if you are working on that kind of problem, you can also take some time to look at this particular library. Okay, and this is the result, and obviously the boosted decision tree was the one that performed the best, let's say. Okay, I ask you for who from you have heard about and who's an expert on the GAN. So if you know that, you can have you can take some break to check your emails or Facebook. But for those of you who has no idea what it is, I just wanted to give a very brief introduction to the problem. So okay, the previous model that I described is the predictive model, which learns the conditional probability. So what was the conditional probability in this case? So we've got the input. So there was an input from the detector, and we wanted to predict the class of the particles. Now we've got so the second type of the models is the generative models. They are trying to learn the joint probability distribution. And how we can achieve this? So one of the ideas that can be used to learn this joint probability distribution is the idea that was proposed by the good fellow, and it's called the GAN. And roughly speaking, the GAN consists of the two neural networks. One of them takes the noise and possibly additional other inputs and generates some image or something, let's say. And then we've got a set of the real data, and there is another network which needs to distinguish whether this is a real image or the real sound or real something, or this was a fake. So these two networks play some sort of the min-max game, and they're trying to beat each other. And from the mathematical perspective, this is the formula that they are using to minimalize. Okay, so I just wanted to show you the very nice example of the GAN. So it would be great. Okay, so I remember when I was back in the secondary school and my teacher wanted me to draw something, I would be really pleased that I have that kind of tool. So I can draw some cartoon, and it will generate the beautiful image of, let's say, as a tree, a snow, or something else. Okay, so this is just to give you a reference. What is the capacity, so possible power of the GANs? And this slide that I'm showing to you was done by NVIDIA. Okay. So why I'm talking about the GANs? So we also decided, so we as a LHCb collaboration also decided to use GANs for the fast colorimeter simulation. In high-energy physics, we love Monte Carlo because we use the Monte Carlo to compare the data that we are collecting with the model, with the theoretical prediction. But the problem is that Monte Carlo simulation required billions of CPU hours and constitute more than half of the LHCb computing resources, which cost like $1 billion of francs or euros, dollars. And one of the most important, one of the hardest part of the simulation is the simulation of particle shower in the calorimeters. So this is the detector that needs to get all of the energy from the particles, and from this you can estimate the energy of the particles. And this, okay, so the idea that we are trying to do is to replace the Monte Carlo simulation with the GAN. And if you wanted to know more, obviously in every single slide, I put some reference, and there will be last slide with all of the papers that I used to build this presentation. Okay, so what we've got, so what is the input to our generator? So we've got noise. Obviously, the noise is like a most important input to the GAN network. And we've got also the input vector, which is the parameters of the particles. So we've got like a energy, momentum, momentum. And then our this discriminator generates the image. So the image is like an output of our detector. And what else do we have? We also have the simulated by our Monte Carlo library called by our Monte Carlo library. And then there is a discriminator that needs to predict whether this is true or fake image. So basically, we put not only the noise, but also the particles parameters. And here are the results. So, okay, so now I remember. So the library that we are using to generate Monte Carlo is called GAN4, and it has implemented all of the features of the detectors, basically. So this was the images, the result in the calorimeters that was generated by the simulation, and this is the one that was generated by our GAN model. So as you see, these two images are very similar. Still, the study are still ongoing, but these two methods give the very similar outcome. But the GANs needs like a 1/5 computational resources than the usual technique. Okay, so there is another image that shows you the comparison between these two methods. So this is really hard to see, but this is like a distribution between all the kaon and pions, and the dashed line represents the distribution that was generated by the GANs, and the histogram, and the remaining is the one that it was generated by the GAN4. And there is no discrepancy between these models, which is great, I would say. Okay, so I'm going to talk about probably the last, one of the last application, and this one is very close to my heart because it was a part of my PhD thesis. 250 microseconds. Okay, so we need to. So as I said, we don't want to keep everything. We don't have that much of resources. So that's why we need to make a decision whether this particular event was important for us, interesting for us, or we just wanted to reject it and forget forever. So the time that we've got, the time that we've got is about 2050 microseconds per event, which is very limited one. And we don't, in the current implementation, we don't have a GPUs. So this is just to give you some reference. And what is the reconstruction? What's the event reconstruction? So we wanted to know the trajectory of the particle. So how we do this? So we put some tracking stations. So this is like a sheet of the paper, and when the particles interact with this sheet of paper, they lost something like we call this a hit, but you can think of this like a hole in the paper sheet. And in each collision, we've got roughly 200 particles created. So we've got like 200 tracks, and we need to reconstruct each of these. Okay, and we need to make track reconstruction faster without performance loss. Okay, so this is something. So now I would like to continue this to explain what type of the tracks do we need to deal. So basically, so this is our. I hope that you remember the schematic view of the detector. Right now, I'm just keeping only the okay, this is probably not readable, but I will explain it. Keeping the only part that are important for track reconstruction. So this is the velo. Velo is our vertex locator. It is located in the area where the particles collide each other, and there we've got also put some tracking station. So the tracking station is a silicon strip basically silicon strip detector that has a very good spatial resolution. And we put one station before the magnet. There is the bending magnets that, okay, why we need the bending magnets? You can ask this question. So you need, when you wanted to estimate the momentum, you need to somehow bend the trajectory of the particle. Otherwise, it will move in the straight way, so there is no way to get anything useful from that. And there is a set of the stations that are located downstream from the magnet. And and what is important, this system, the reconstruction, you remember this, right? How many tracks do we need to reconstruct? We've got only 250 seconds, microseconds, sorry. And it needs to be very reliable, I would say. Okay, so what is the important, so what I was working on, so there was a second type of the track that don't have information about the vertex. And we call this downstream track, and the track of daughter of long-lived particles. Okay, lots of hard word. So what we consider as a long-lived particle, so you may see like a 1 year or something like this. No, we consider the particle is long-lived if they can travel something like a couple of centimeters. And it's travel with the speed of light, so you can, from this you can divide one number by another, and you can find the time that it's alive, a couple of picoseconds. And okay, so how we do it? Okay, so I'm talking about this downstream tracking because I was involved in this processing. So what are the key components of this algorithm? So first part, we reconstruct the tracks that are the tracks using the hits that are located in this T station outside of the magnet. You see the multiplicity of the hits are lower than in this region. It is easier task. So then when we've got this, we need to combine with the hits that was reconstructed in this station before the magnet. Okay, so as I said, this algorithm is seeded by the track reconstructed in the T station, and then okay, so there is from some reason we are not able to reconstruct each of the seeds. So that's why we decided to use like one machine learning classifier that will tell us whether the track seed is a good one or it is something what we call ghost, so which is not, let's say, not okay. And this is the problem related, very similar to the spam detector problem. In spam detector, we wanted to keep every single good mail, and we wanted to reject as much as the spam mails as possible. Obviously, there is more harmful if we remove the very important mail. Let's say that someone get a job offer from Google or Facebook, and the Gmail decided that this is not important mail. So the user will be very unhappy with that. But actually, if there will be a couple of additional mails that was not very important for him, he will say, okay, I can just delete it by myself. And okay, so when we've got this, so we are classifying whether the track segments are reconstructible. Then we've got, then we are looking for the matching hits in this section that is before the magnet. And then there is another machine learning models currently implemented as a deep neural network that for each of that select only the tracks that are good based on its score. Okay, so I would like to show you the final result, and then I will give you some. If you are an expert on the machine learning field, you can take another rest. And if you are not, I will give you some learning that I gained building this model. So first is the problem. So I used for the training this model. I used this classifier. I use the data, the simulated data that contains particles B, particles decaying to JPCKS, which is not very important to you. I used about 2 million of track seeds, and the final score that I obtained was measured as an area under rock scale is 86. And this, okay, so you remember, so we are operating in this area of the rock curve. We need to keep all of the true values and remove as much as fake as much as possible, spam detector. So we were able to remove 30% of the fake T seeds. Okay, so how we achieve this result? So first of, okay, so if you know how to play with the hyperparameters, you are expert on that, you've got a break. So okay, so if you're not, I will give you some explanation. So what are the hyperparameters? So imagine that we've got a pretty old TV set, and we wanted to tune it, we wanted to watch something. So there is a couple of knobs, and we need to find the best configuration that will give us a very sharp view. So what are the strategy to adjust these knobs? Okay, so the easiest one is to split the possible space into the equal distance, and for each of the distance we evaluate the model. But this one has a huge problem. This one has a huge problem because if there are two hyperparameters, one is important, the second one is not important, we are not probing in sufficient places the one that is important. So the better one is the random search. So we are randomly pick the value from each of the hyperparameters and we evaluate the models. Okay, so what are the problem of these two mentioned methods? So each of these methods doesn't leverage the previous evaluation. They are just blind for what was achieved as far. So we can get at something a little bit better. And if you are playing with if you are building your machine learning model and if you are working on the hyperparameter optimization, which you should do, I would recommend you to go directly to Bayesian optimization. So this is the model that that store the previous evaluation to make a better guess. So so let's say that we wanted to so it models something like a score conditioned by the value of the hyperparameters and use the Gaussian process. This is a written Gaussian process as a surrogate model which model the score. And there's another thing that is called the acquisition function, which is the function that balances expression and exploitation. It shows you in which point we should probe next. Okay, so another thing that is very important when you are working with the machine learning model. So most of the time, what do? You just calculate the overall score, something like accuracy or maybe ROC or something else like R1. And based on the entire test set, and you are claiming that this is your final score. And you are very happy because sometimes you get 90% on 90-something and say, yes, we build a very good model. So is it true? So is it sufficient? So let's say and sometimes model makes a very critical prediction, like a trigger crucial action, like cancer treatment. So if our model makes a wrong decision, the patient will not be treated and may die because of our model, or someone. Okay, and as I said, sometimes this. Okay, so take a look at these two examples. So the people wanted to try build a classifier that will classify between the husky and the wolf. And it turns out that they not build a classifier that looks at this particular animal, but instead they build a snow detector. So the classifier said, okay, if there is a snow, there is definitely a husky. Okay, so what are the approach to try to understand? Because except of the wide adaptation of the machine learning model in the various areas, in many cases we have no idea why they are making some particular decision. And I know that there will be another talk on this particular topic in like 6 hours, so there will be more technical stuff about this, but I will just give you the two methods that I use in my study that will allows me to be more convenient that the predictions are proper. The first one is called the LIME, Local Interpretable Model Agnostic Explanation. So first of all, in this particular method, we need to pick the model that is easily explainable by the human. And the one that is the easiest to explain is the linear regression. So we know when we've got a linear regression, we've got the weights, and based on the weights, we can set the feature importance and so on. So what we are doing? Okay, so we picked some random, maybe some random examples, and we are looking at the surrounding of these examples, and we trying to make an interpretation in this area. So this is very similar to Taylor series. So Taylor series is like an approximation of the complex function to a linear form or to some order of magnitudes. And okay, so this method minimalize this function. So one of the function is make the fidelity of the interpretation, and the second one interpretability. So first of all, we need to have a model that we can still get some knowledge from it. Okay, and this is two exemplary results that I wanted to share with you. So we picked two classes. One was the fake seeds, and the second one was the true one. And we wanted to know why they was classified in such a way. So first of all is, let's say, this false one. We see this, okay, I don't know if this is readable, probably not. The first feature, the one that is appears in here in this first line, is the number of the hits. So which should be pretty important, pretty reasonable. So if we've got small number of the hits that build the track, it is more probable that the track is a ghost one. So we should exclude it. And this, okay, so these methods generate explanation, and then you can compare with your understanding of the problems, and then get something inside what is going on with the model. It is very useful when you're debugging something, when you build the model, and you've got some particular example was classified incorrectly. Then you can think, why was there? Why the classifier made this particular decision? Okay, because one of the features has value in this range. So is it okay? Maybe with the method how we collect the data is not proper, or maybe something else. This is like a good method to validate. Okay, so now I would like to show the second. I don't know how much time. Still have 5 minutes. Okay, so the another one is called the SHAP. It's something related to the Shapley value. I don't know who from you have heard about the Shapley value. The Shapley value is a concept from the game theory, and roughly speaking, let's say that we've got the game, consider the game coalition game. So we've got like a couple of players, and they need to decide whether to establish the coalition or not, or to take part in the coalition. And then there is a question, what should be the outcome? So how we should share the payoff of this coalition? That would be the fair. So which means it should be proportional to the influence that particular player has on the coalition. And the same idea we can use to calculate the feature importance. So this is how the Shapley value. This is a pretty complicated equation, but basically what we are doing, we are calculating the value of the game. So let's say that the score of the classifier when the particular feature is taken into consideration, minus the value when it is not in the coalition. And this idea gives you how important some particular feature is. And this SHAP is a package written in Python, so you can very easily use it. And this SHAP gives you a couple of nice plots. So first of them is the overall feature importance based on the SHAP value. So each of the points represent one data point, and the color is proportional to a value of the feature. And so the second idea that the second type of plot that you can create using this SHAP value is the dependence plot. So you've got SHAP value versus the value of the feature, and then you can somehow compare your understanding of the problem. So let's say that we've got so in this case there is a high square fit quality of the track, and then we can, if the high square is a pretty pretty low, we see that the value of the classifier is low, which is okay with our understanding of the problem. So this is another way how you can debug the problem. Okay, I don't have unfortunately time to cover this one. Okay, I would like to invite you for the poster session where my colleagues who is sitting in here will be talking about his project. Okay, you probably heard about the Velo, as I told about the Velo. Velo is a silicon strip detector which looks like this. And in this particular project, we need to do a calibration. We've got about 180,000 parameters that we need to channels, sorry, that we need to monitor. And Maciek will be really happy to tell you more about this. So today, probably he will be here. So. And okay, conclusion. So LHCb is pioneering the application of machine learning. So we leverage machine learning in many various areas such as data analysis, reconstruction. And one learning from this particular talk, please do not treat machine learning or deep learning model as a black box. Try to understand, try to use some methods to verify the prediction. Okay, so this is the bibliography. So if you wanted to, so this is like a set of the papers that I used to build this presentation. And thank you for your attention. And thank you.